over and above the amount required for minimum fluidization will start going through the bed in the form of bubbles. Okay, so here you have the particles you want to dry, you have the air, incipient air going through it, and then you also have bubbles going through it. Some of these bubbles may trap some of these particles, but mostly it will have the air inside. Okay, so this is a typical drying system. The reason why I wanted to show you this because it is very important, especially in drying applications, how these bubbles behave. Okay, and we're going to talk about this in a little bit more detail shortly. But if somebody says you're working somewhere and you need to propose a dryer, and you say, I think we're going to use a fluidized bed dryer, and your supervisor, your boss says, well, tell me why a fluidized bed. What are the advantages? And you should be able to list all of these that you're seeing in front of you. First one is high moisture removal rate. It it efficiently removes moisture. We talked about this. High thermal efficiency. Remember, the air you're putting into the fluidized bed, you have to spend energy, you have to spend money to heat this air. So, how much of it are you transferring? How much of that thermal energy are you transferring to the bed of solids in order to remove moisture? So it's the efficiency of this thermal process is quite high. It's not great because I'm also going to list it as one of the disadvantages that the hot air you're losing, unless you use it for another application. It's uniform drying. I told you about, of course, it's the better mix the bed, higher the uniformity of properties of the particles in the bed. It's fast drying. Relatively, again, examples I gave you, if you were to do it naturally, just exposed to radiation, it will take much longer. However, here it will be very fast. And of course, the other example, it will never be uniform if one layer is above the other. It will require constant agitation. Bed temperature is steady, stable. So because of the large, again, thermal mass you're creating in there, material transfer is easy. Fluid bed makes it easier for us for having a fluid-like behavior, as we talked about it, that it will obey all the hydrostatic laws. Versatility, again, you can dry wheat one day and the next day you can dry something else. It's all possible within, of course, a prescribed range or particle classification. Low maintenance cost. We touched on this earlier that because there are no moving parts within the bed, the only rotary piece is the blower that is providing you with the fluidization air. Control is relatively easy, and you can add some automation to it, which will be required, but you will find out why it will be advantageous to add some automation to them. And it is quite adaptable. It can be integrated. You can remove the moisture on one hand, and you can use it also as a cooler or mixer or coater or classifier in various forms and shape. Okay, put this here so I'll know my time. What are the okay? The boss said really good. Okay, sounds very good. attractive, but what are the shortcomings? Are there any disadvantages that we should be aware of before we invest some good money into this? And you should be able to say, well, as again, when we are putting a lot of air through here, and you can easily calculate the amount of energy you need to heat this air to, let's say, 60 Celsius, 65 Celsius, and you're putting through, I don't know, at least a few tons of air per hour. So it costs you money, but then you throw this air out of your at the exit because you need to continuous to provide air. So it's a continuous process, whether it's batch or not, but still air must be moved. Generally, solids must be fluidizable with average diameter less than 10 millimeters. Okay, 10 millimeters is 1 centimeter, about this size. It's a fair size. Could it be larger? Yeah, but you will run into a lot of challenges. Um, there is something we didn't talk about it, but I am hoping that you're familiar with the term attrition. Attrition is because it's a bed of solids when, especially if they're not perfectly round, when they touch each other and they break pieces off each other, okay? Attrition. Therefore, you lose some of your material, or sometimes they touch each other and then they can be fragile and they break into smaller pieces. And if that happens, it's much faster, the terminal velocity, and you lose those, and also you lose the integrity of your of the product. And because of that, and for a variety of other reasons, you will need a dust removal equipment, usually in the form of cyclones or bag filters, or depends on it. So your boss said that's pretty good. I am convinced. So we're gonna take this to the next level and invest some money in there, and we're going to design and build and operate one. Then you'll need to decide what kind of bed you want. Do you want a batch dryer? Means you will load it, run it, drain it, load it, run it, drain it, or you need a continuous one. So batch dryer, usually if you have the range is not bad, but still a smaller one between 50 kilograms per hour to 1,000 kilogram 1 ton per hour. These could be also mobile. Okay, you can put them on the back of a truck and take it to the field, so long as you have a diesel engine or engine running and providing you with the rotary function of a blower. You can take it to the field and collect it there. Uh, uh, this is suitable batch operated upstream and downstream processes, or when multiple operations, required for granulation, coating, sifting, anything. Uh, Airflow and temperature can be minimized again in order to save energy, or you can modify it. Um, these kind of batch fluidized bed dryers, you can also, even though I say mixing is great, it's usually depends on the type of particles. You may not have well mixed one. We talked about it. You may want to put some mechanical agitators or other means, like a shaker, vibrating bed, and things like that. It's a lot easier to apply those if it's a batch operation. And design is relatively simple. See, you have your particles, grain, whatever you want to dry through here. You use, in this case, a little high pressured air because it won't go through it, and so you have to kind of provide a pneumatic transport like conditions to push it through here, comes downwards in the opposite direction of the hot air, and they're dried within a prescribed time period, and then poof, you take it out and then put another batch. Continuous dryers, however, uh, which are desired for larger loads, could be in two different categories. One category is the back mixed dryer, and please pay attention to the two. One is back mix dryer, the other one is plug flow dryer, fluidized bed. Here, this is where the dense bed surface is, okay? And solids are fed into the dense bed, okay? It depends on the density and size and everything, but this is one design that's into the dense bed, and the other one, in this case, plug flow, is to the freebore. Okay, and so here, as they are falling, the surface moisture is very quickly removed, and then here inside they will have more time, residence time, for the inherent moisture to be driven out, and here you collect them. If you have you start with smaller surface moisture, you need your dryer mostly to remove the moisture that's trapped inside the particle. Then you want it to spend more time within the dense bed, okay, and to benefit from all the agitation and mixing and everything inside the bed. So flow pattern, of course, in here differentiated based on the flow pattern of solids in the dryer. And this includes the plug flow and back mix flow. Inlet and outlets, they have an inlet for moist material and outlet for dry material. That's both, we see. So that is the beauty of the continuous operation. The batch one, as I said, you operate, then you stop, you unload, put the fresh batch in, and then you start again. Here, it's continuous. You have one port for material in, and the prescribed time, whatever, and then you take the dried particles out. Viscous or cohesive materials are a lot better handled here, especially if they need pre-drying. A reverse mixing fluidized bed or a continuous back mix fluidized bed is much, much more appropriate than a batch one. Okay, I'm gonna uh, maybe just spend a few minutes here. These are interesting design. Um, this is pulsed fluidized bed dryer, and it pulsates. The instead of feeding the air continuously, you pulse it. And there are reasons behind that. Pulsation helps break um, both slugs, but also helps better distribute particles. And also, you have different chambers. Like part of the bed here is fluidized, part of it is not. Particles that are in the non-fluidized part, they are able to, again, because it's still in a hot environment, release or allow for the inherent moisture to move towards the surface. So these are a little more detailed, but nevertheless widely used in industry. This is the hybrid one. Again, it has different methods, and part of it is fluidized, part of it is not, for the same reason. Okay. Um, Superheated steam is better for some applications that need to be quite sanitized. So let's talk about things that you love to do, and how do you calculate heat transfer and mass transfer in this case. Remember, we're going to see some modeling and calculations and everything. The objective is, I am asking you, I said, I am in continuous need of drying my crop. It will come to you with making it up 40% moisture content. I want you to remove the moisture down to 10%, 8 to 10%, so I can then sell it. And you need to calculate precisely how much time you will need, how long they need to be dried, at what temperature, so that you can ensure that the product is at the prescribed level of moisture. Okay, so heat transfer, as I mentioned earlier, hot air basically heats the particle and enables mass transfer. Moisture, again, is removed in two steps that we explained. I explained a little while ago, and then all of these are taking place simultaneously. Okay, the removal of the moisture from the surface. At the same time, the particle is being heated, the capillary moisture is moving out to the surface and is being taken away, and you're ensuring a uniform environment for it to take place. So, you've taken, I'm assuming again, you know your heat transfer and mass transfer, you know your transport phenomena and UNIDOPS, that the total rate of heat transfer from the bed to either a single particle or bed of particles, let's say a single particle, you need to have the heat transfer coefficient. In drying applications, um, it is mostly convective heat transfer as opposed to combustion that you have to take radiative because of lower temperature. We're quite comfortable. We're quite fine just using a heat transfer coefficient that is dominated by convection. And we have temperature of the gas, of course, air, and temperature of the particle. And then you can calculate the total heat transfer rate. And for the heat transfer coefficient, of course, you have to know the particle Reynolds number. Particle Reynolds number will give you the particle Nusselt number. Then from Nusselt number, you have the thermal, the heat transfer coefficient. And this is again done in a way that in an almost isothermal conditions, if you can, for which if you insulate the bed so that there is no heat losses uh, or around the or surrounding the bed, and all the heat is trapped there for one purpose, to be transferred to the particles. Okay, and this is the most general equation you can use, and you have to know the Reynolds number of particles, Reynolds number within the tube or the vessel, which then the characteristic length is the diameter of the bed, whereas the particle Reynolds number is characterized by the particle diameter, and then you use those. The Throat number, Reynolds number, Nuss number, they will all help you to determine the total heat transfer by through the estimation of the heat transfer coefficient. Okay. As I said, in fluidized beds, there are no, like, because of the nonlinearity of the whole thing, you have to rely on a lot of experimental data. And that's where, if you're wondering where did these numbers come from, they are all obtained through experimental investigations and data provided in order to obtain these correlations. And the mass transfer takes place in a similar fashion that um, as I mentioned, you have to um, drive the moisture out here and then wait until you have the other part moved. This is a constant pressure operation, and I did not mention it earlier on, but it's not a pressurized vessel. It's operates under atmospheric pressure, and for the mass transfer, of course, we use two fundamental equations. One is the conservation of mass. Whatever total moisture goes in, that moisture will go out. So it doesn't go anywhere else. So where does the moisture come from? It's moisture within the particles plus whatever moisture, even though you're going to dry the air, you put in there, and that will equal to the total moisture that is coming out with the exhaust air. And then you apply energy conservation and the enthalpies and masses, and this from the particle, from the air, will be equal to all of these plus heat evaporation. And as I said, if you don't have perfectly insulated, then you will have some losses going out. You have to account for this. Then you can calculate heat transfer due to evaporation in this fashion. So let's then start looking a little bit closer in more detail. What do we need for this to operate? I need a feeding system. I need either a mechanical conveyor belt system, or I need a system that I will need to aerate for it to move easier. So you'll decide on this one. Of course, you need the main vessel. You will determine that based on let's say continuous operation, the load is given to you by the customer, and then that will help you. You do your calculations to determine the diameter. Usually, it's a lot easier if it's cylindrical, or it could be rectangular. Rectangular ones are easier to manufacture because you just weld the plates. Just depends on however you want to do it, but you will then be able to design the size of it. Then here comes one of the most critical aspects is to decide on the distributor type. Okay. What type of distributor you will need. Remember, we said distributor is essential to provide the bed with a uniform distribution of air and bubbles to provide the best mixing environment, and at the same time support these particles or prevent them from falling downwards when the bed is stopped. So then you need the plenum chamber. Oops, where did I go? It is important. Usually it is shown as empty, but if in your, I don't know, in the lab, if you saw it and if you have it, we call them Russia rings. It's all uh, used like a grinding machine in ensuring that air entering is already distributed uniformly, and you've taken care of all the inlet losses and whatever, that the air is already entering the distributor plate in a uniform fashion. Then you will design your exhaust system, ensuring that, again, for example, the slope is this of this cone. If you do it this fashion, is important. What kind of angle you will use, and the exit losses here that we take it into account. And if you need to control it two ways, you may want to put an exhaust fan in there, but usually you won't need it. And do you need to clean this air? Then you will need gas cleaning apparatus there. Okay, so these are the basic elements of a fluidized bed dryer that you will be thinking of. You'll either manufacture them in-house or you will order them through suppliers. So, as I said, if you have fine particles, they will definitely escape. You may want to either if you're doing this in a plant, you don't want a plant filled with dust and everything. You want it to be in a clean environment. Second thing, you may want to collect those because it's money. You may not be able to sell those at the same price as this intact ones, but you may also still sell it at a discount. So you don't want to throw your money out. And you use, as I said, cyclones, other means to capture these fine particles. You need to, of course, ensure that whatever you do, it will cost you the minimum pressure drop throughout the bed. The higher the pressure drop, the more the higher the energy requirement for your blower. So make sure that your design will. I mean, you cannot escape the pressure drop that will be needed for the minimal fluidization and at the upper. Remember, you need that delta P until you overcome the bed resistance. After that, it is flat. So make sure that you're fluidizing in an efficient way. And you will definitely use, even though, of course, there's no stoichiometry involved here, but you will use, the more air you use, the faster the heat transfer rate, but up to a level. When it comes to the distributor, and again, you will ensure that it is providing you with a uniform mixing across the bed. Usual rules when you're doing this, you follow like rule of thumb: 30% of the pressure drop for upward and lateral flow, and 10% for downward flow distributor plates. You will also, you're not just doing this from the scratch. In a fluidized bed, it's a through flow fluidized bed. This is basically like evaporation rates. It's depending, of course, what you're trying, but so you can reach up to, like, this is, of course, sorry, it's in British units, but quite high evaporation rates you can achieve. So you know that you're working within that window. I want to talk about slugs. And why do I want to talk about slugs here? Uh, this is a bed. We call this is freely bubbling. You have bubbles formed at the distributor, just right above the distributor plate, and they start moving upward, and some of them will coalesce with the other. Normally, they will grow in size. In certain cases, they won't, but then depending on the size and of the particles and size of the vessel, and we talked about this, they may coalesce, they will join, one will join with the other, and then will form a slug. And then when the slug is formed, your bed is basically is defluidized, and we will see this shortly. Why am I saying this? I want to take you back to a Geldart's classification. Okay. And here, look at the particle size in micron. And we said we have mostly grain around 1,000 micron. And this is the density. And it is quite possible that you will be in spottable region according to Geldart's classification, and that your particle will be a group D particle. Okay, so look at all these. These are all experimentally obtained. Look at these. For example, let's see where rice here, for example, here, rice. You see, it's here, uh, but if you want like big S, it's right here in the spottable region. So you have to take this into consideration very seriously. So most likely, they will be group D particles. Every drying application that I have involved or designed, they fell into the group D particles and larger than around or larger than 1,000 micrometers, and that's the case. It is a spottable application or particle. Uh, Very dense particles, in addition to the size, can also be characterized as group D particles, even though they could be smaller. Okay, like in iron ore, for example, processing, that will be the case. So, if that is the case, it limits mixing. Why? Uh, Let me take you to this video. As you saw in the video, short video, when the bed spouts, you saw the core place where a lot of convective air movement is, and convective heat transfer, mass transfer are taking place. And around that, it is like almost like a fixed bed, and particles are moving very slowly. So, as I said, in certain drying applications, you may want to use a spot bed because um, you need to keep the particles longer, the grain longer in the bed, but not necessarily subject to the airflow. So you provide airflow in a way that it's only enough for the core, but it's not needed surrounding, so that they could stay there longer and have the moisture removed through diffusion. Because doesn't matter, and once they reach that stage, how much they are exposed to the air. So that is the case. In some cases, however, you don't want a spouted bed. You want a uniformly mixed one. So you have to be careful, mindful about the size of the particles and the group of the particles. And if you don't want a spouted bed, you will take some precautions like controlling the air, but also you may want to put some mechanical lures and other means by breaking those spouts up, then into smaller bubbles, and then promote more mixing. Okay, so for that, you will need to figure out the minimum slugging velocity. This is the simple correlation that takes to account the particle, whether they're spherical, cylindrical, so the shape factor is important, and then the frequency of slugs. You will need to know how frequently they form, and with that, you will be able to calculate a minimum slugging velocity. Okay, how about a break? It's been an hour. Let's take a little break, 5 minutes again, and then we'll reconvene. Okay? Then we'll talk about distributor plates. Okay?